In this video, you will see my call with Yuri, and Yuri is going to explain how ground vias, or they are also called stitching vias, how these vias are helping signals to travel through your PCB. So let's start. Here is my call with Yuri. So what we are going to talk about today?
We are going to talk about vehicles and vehicle localization and vehicle localization property. Yeah, the board itself looks really simple. It's kind of right here you can see that it has a couple of vias or a couple of paths for source, signal source, and or transmitter and receiver, or measurement points, and so on. And it has a via in the middle, and basically the rest of the board are just planes. So that's a simple board. And let's first start without the stitching via, exactly like it is.
So what does it mean we are going to start without stitching via? There is no like easy way for return current flow through this circuit?
No easy way.
And in this example, we are going to show how important it is to place a ground via close to the via where we are changing layers when we are routing tracks.
Exactly.
Okay, so let's first simulate this one. I'm really curious to see why it is so bad not really having vias.
Okay. That's current flow density here at 1 megahertz. I don't know what frequency was used in your simulation, but I noticed in your simulations that currents are kind of penetrating through the planes. And at first I thought that maybe it's kind of some bug or what it is. But then I put it into the simulation at 1 megahertz, and you can see currents. This is instantaneous values of current flow density in amperes per meter. And you can see current flowing on a trace and current flowing below the trace. So how to see below the trace, I can simply cut the trace and just see this is the current below the trace in return path.
So basically under the track, we have solid ground plane, and the return current for the track is returning directly under the track on the solid ground plane. Okay, but I would expect something weird happening where the via is placed.
Well, there is nothing special on this surface of the board at 1 megahertz. But if you look from the other side, let's just take a look. And I essentially cut it to just one plane. If you look at the other side of the board, yeah, that's exactly what happens. So what happens, essentially, the currents flowing all over the board. We can take a look at the arrows, which...
this is cool. I never thought about this, that basically this return current will spread actually on the other side of the copper.
In this case, yes, it spread on the other side. At 1 megahertz, the skin depth is, and I brought, I don't remember the number, so I brought the marker here. So at 1 megahertz, it's 2.6 mil. And essentially, the current, and the current here in the middle, is not large to be visible on the other side of the board. So let me just switch back to color map. So we don't see them down to minus 60 dB. We see them only on this side of the board. So there is no reason for current to return somewhere here on the top plane. But then when you start crossing the planes, that's where the current has to, well, they say find the return path, or in reality, it's just a process of wave propagation through the structure. So it gets into this interplane area, and then
So basically, the return current will be traveling from the bottom side of this solid ground plane to the other plane, which is under, then to the other plane, which is under, and then basically it will appear on the, exactly.
Exactly. Every plane here will have current on the both sides when you go down, except the top one and bottom one. The top one, surface of the top one plane, or the top plane and the bottom one. But notice another thing. Notice one more thing here. If I how this current below the trace flows here, it has some substantial delay. You can see if you compare it with this side, it flows below the trace basically in phase. But
so basically what we are seeing is it's sine wave, correct?
Yeah.
So it's not square, it is sine wave. Yeah.
It's a sine wave here, 1 megahertz. Essentially, yeah, it's a frequency domain analysis.
And yes, it is in phase. So what is traveling on the track, it is also returning back. But here it is different. We can see,
yeah, it goes back with substantial delay. It may even change the direction. On the top, it goes in one direction. At the bottom, after this wave gets through, or energy gets through the plane, it may change the direction. So the current is essentially not so useful concept in this kind of tracing where it goes. So if you switch to 1 gigahertz,
I would like to before we switch. So basically, why is this happening? Because it is going through the capacitor and through the structure, so that's where the phase will change, or why the phase?
The phase will change in the metal. Metal has higher conductivity, so and it's conductive media, and the energy within the metal goes actually into the metal to the other side. So if along the trace energy travels in the space, as Ralph Morrison said that PCBs have traces in spaces, and your signal travels in spaces. So your signal travels along this trace in the space along the trace. But as soon as you get in the metal, there is not the energy of the signal goes perpendicular to metal. It goes to the other side. So that's what you observe from this side of the board, that the energy gets through the metal, through this, in this case, it's 1.3, 1.4 mil metal. And at 100 megahertz, the skin depth is larger, like 2 times larger than thickness of the layer. So we can see this current on the other side. So there are 2 currents overlapping here. One for return, for V return current that is spreading all over the board. And another is return current from the trace. You can see it. And you saw it in your video as well. So but what happened at 1 gigahertz?
Okay, let's see. Oh.
Boom.
Oh.
Exactly. Exactly. You still have return current on this side. So and we can see it in as arrows, for instance. So the arrows are in completely opposite on trace and on the bottom. So you can see those are going this way, this going this way. And then sine waves, they go up and down, up and down. Okay, but no trace image on the other side. And now, how you can tell where the return current now? Is it through those teaching vias over here, or where it is? And so it's not clear. It goes through basically 2 things. One is displacement current between the planes, and another current through those stitching vias through the parallel plane kind of modes. So the processes that take place in parallel planes. The parallel planes, they work not like a capacitance anymore. Because if you can see the currents in capacitance, you essentially have same current on both surfaces, but right here it's a more kind of unpredictable process.
So this is basically how the resonance will happen, for example, between planes?
Exactly. You inject the energy, it goes into the interplane area and forms the resonance. So at some point you hit the resonance, and at rather really low frequencies. If your via doesn't have stitching vias, energy spreads, return, basically the impedance of return path defines all this. And the impedance includes the effects of the plane. So it may go very high, very low, depending on resonances in the planes and other components connected to the plane. So there are two, remember, there are two stitching vias on this side. So let's go down a few planes on the other side. So on the other side, we observe pretty much the same picture. We got some energy getting through at 1 gigahertz. We have this process at the mass bottom plane right here. And if we switch back to 1 megahertz, we will observe essentially the same process at the receiving end.
So this is basically the bottom track and the ground plane above the bottom track.
Yeah, it's like right here we're looking from top. We look from top, and then we go and look from the bottom, and we see much the same process here. So, well, let's try other scenario, and we put a stitching via closer to it.
Before we continue, I know people will ask what software you use for the simulation. It's your software.
Symbior software, Symbior electromagnetic signal integrity software. This runs Symbior 3D-TF solver with license Symbior Complete.
Okay, so now there is a via in the middle of the board. I see it.
Via in the middle of the board.
And it's connecting the ground planes.
Yes, and via are tiny. You don't see it again on the top surface. You cannot really guess that there is a via over here. But when we do the same trick and move this, cut out the top plane and cut out actually just the bottom plane, just like this. So you can see the difference. So now we've got, if in previous, again, this is 1 megahertz, very low. We still have image of current, image in a sense of we have some traces of the current below the trace on the other side of the plane, and we can also see this kind of. Let me just switch to arrows here, and you'll see.
Yeah, we can see the current, return current tries to go to the ground via.
Through this stitching via, yes, that's correct. So that's where the currents are high.
This was my mistake in the previous simulation. I didn't have a look at the bottom side of the copper. This is something really interesting, because I never thought that actually I need to have a look at the bottom side of the copper.
And frequency matters as well. So if you took just 1 kilohertz, for instance, measurement, it's going to be again different. 1 kilohertz. So I have some simulations done at 5 kilohertz in my demo videos. That's completely different picture you may see. But right here I started from 1 megahertz, so it's a kind of more practical range, frequency range, and also did 1 gigahertz. Just
with 1 gigahertz, the stitching via in the middle, it doesn't really help much.
No, there is no continuous currents between those. So if you compare this one, it's 1 megahertz, essentially they work together, 1 megahertz. But at 1 gigahertz, stitching via is just a part of parallel plane structure, parallel plane, which essentially it's not resonating at this point, but you see some harmonics of some pattern here. That at 1 gigahertz on this side, again, you see just the return current below the trace. And on this side, we see something completely different. If you go one plane down, just go one plane down like this, you'll see it on both sides. You'll see pattern like this.
So I think there are four planes in the stack up. There is a ground plane, and then there are 2 power planes, or I don't know. No, 4 ground planes. I think there are. I don't remember.
There are 4 ground planes right here. I reduced it to just let me. I left just 3 to illustrate the idea.
Okay.
First, it's simulation faster. I can simulate with all planes, but realize that it may be too much.
Okay.
First, it takes a lot of data on my disk, this visualization part. And second, it does not illustrate idea.
So we only wanted to see basically how this energy will travel between ground plane, some other planes, and then the
yes, a couple of planes in the middle that basically give you the idea of what's going on. So how currents are distributed on those. So it gives the idea that well, something really bad happening.
So basically, this is telling us that this is basically why it is important to place the stitching vias close to the place where we are changing layers, because if they are too far away, they are doing nothing for higher frequencies.
Yes, that's one of the vehicle localization ideas, that everything, this distance, electrical distance, matter. In this case, 1 megahertz, it's okay. You get your design, you keep working, but at 1 gigahertz, no. So
but even for 1 megahertz, you can see the field is spread through half of the board. So maybe for, I don't know, sensitive analog applications,
it's not field. It's a surface current. And that's essentially illustration of how surface current may be not really representative or not really illustrative of what's going on the board. So you may use different metrics to, and I'll show you more detailed example, how comparison example.
Yeah, but still, it is saying us that these fields are spread all over the board, and if you have some sensitive circuits there, then these sensitive circuits can be influenced by all these fields, which are
exactly. If you have current somewhere, there is a voltage drop at this, and that may generate, create multiple problems. So, at 1 megahertz. The whole board is still much smaller than wavelength, so it will not act as antenna, but then you can pick up the voltages through current drop, through the resistance of the metal, so you'll encounter some voltages at unwanted locations. It's mostly MCMI problems, so not signal integrity. But then when you go up in frequency, it becomes signal integrity problem, because of VIA start dissipating the energy into the center plane. How it ends up, nobody knows. So it may dissipate, really dissipate and hit, or may return into your signal path or other signal paths and get signal distorted, which is the worst kind of distortion that it's very difficult to predict. have those effects like taking place not locally, but rather at some remote locations where you lose energy at the via, but then it appears somewhere, someplace else. So to prevent it from happening, this is again one of your design.
So this is the third example.
Third example. Put a stitching wheel over here.
Can you show where the via is so everyone can see it?
It's okay. It's over here.
It's very close to the place where we are changing layers.
Yes. That's the structure. Okay. So very close, and just one. And I'll show you that just one maybe not sufficient. With another way to. But let's take a look first
okay,
at
I'm curious. I'm
pattern.
really curious.
On the much like this, and the other surface now is pretty much clean. So there is a little bit of current.
So this is the bottom side of the
first plane. This is top side.
Yeah.
And this is bottom side of the very first metal
plane. That's big difference.
Yeah, absolutely. That's big difference. And just compare with this one quickly. I cannot quickly. I need adjustments of the for matching adjustments. But you saw that in one in case without stitching via, it took the whole plane. The return current was all over the place. And with via in the middle, it was a return current of 1 megahertz through the middle, and but the problem was at 1 gigahertz. This is at 1 gigahertz. Remember that this side has also vias. There is a return current associated with those stitching vias right here. So those bright spots we see here, they are relevant now mostly for this vias, and this bright spot is relevant to this stitching via, the signal via and stitching via. So it's essentially more isolated or more localized.
So does it mean that part of the return current also flows close to this input and output, or receiver and transceiver?
It does, but you see, in this case, you've got measurement points at the top. So right here, what we observe on this side is a stub, essentially. This is how this, there is a vehicle stub over here. And there are some currents associated with this stub. Yes. And at lower frequencies, it would just take a look.
Oh, I understand. So basically the signal travels to the bottom.
To the bottom, yes.
And that's what we
still,
it
still kind of looks like a small piece of, not exactly transmission line, but two vias, one signal, one stitching. And you can still observe currents on them.
Okay, and on the other side, basically it travels from the bottom to the up. That's why
exactly. The signal here has to travel from the bottom side to the top side. And it uses this stitching via that is nearby. That's why we observe those currents at this location as well. So,
this animation is like really super helpful.
Yeah, it is. I remember when we did the first video with all those signals traveling. That was also animated. You said the same thing, but right here it's relevant to this return path.
Okay, so let's. Now we have fourth example, correct?
I have now. I have another solution created here.
Oh, okay.
Where I basically took just a single via and then try different scenarios with one stitching, two stitching, four stitching, and six stitching. And same experiment for differential. Without stitching, then with one, two like this, two like this. So